I've been told to introduce myself. So very briefly, I'm Sophia Rabe-Hesketh, and the talk is about predictive information criteria for hierarchical Bayesian models for clustered data. And this is joint work with Dan Furr, who's going to be presenting some of this, and Ed Merkel, who's not, unfortunately couldn't make it to the conference. And I'd like to thank the organizers for inviting us. So first I'll define the predictive information criteria, that is the AIC, DIC, and leave one out, and showing the connection to leave one out cross-validation. Then I'll say what I mean by hierarchical Bayesian models for clustered data, and examples of these are mixed or multi-level models, MLMs, structural equation models, SEMs, and item response theory models, or IRTs. For these models, there's an important distinction between marginal and conditional versions of the information criteria. So that I'll describe those, and then Dan will illustrate the importance of making those distinctions through an example to item response theory, or IRT. So what is the target, or what are the information criteria trying to do? Let me first introduce some notation. The likelihood is denoted F. All the responses are denoted bold Y. All the parameters are denoted theta. And the prior I will use P, but I'll also use P generally for probabilities or densities. So what we want, the goal is to assess how well this model predicts future or out-of-sample data, kind of validation data that we haven't seen yet. And if we had this out-of-sample data, how would we evaluate the prediction error of our model? Well, a very popular way of doing that is through the deviance. So that's minus twice the log of the likelihood evaluated at the out-of-sample data. But what do we do about theta if we want to get some prediction error measure? So for the DIC, what we do is we plug in the posterior mean of theta. So we get the plug-in deviance, which is just minus twice the log likelihood for new data at the posterior means of the parameters. And for the WAIC, we do something more principled. Instead of just plugging in the posterior mean, we integrate over the full posterior. But we do compromise by having to use these pointwise predictive densities here. And so we take the posterior expectation of the pointwise predictive densities, and these can also be called predictive densities here. But the real target of the DIC and WAIC is actually the expectation of these prediction errors over the distribution of future data. So for the DIC, that target looks like this. We have the expectation of a future data. But we can't really evaluate that expectation because we don't know the generating distribution of the future data. And we assume that they come from the same true model as the observed data, but the whole point is that we don't know what that model is. And we can't even evaluate this plug-in deviance for one out-of-sample data set because we don't have any validation data typically. We just have one data set. So what we do is instead we use the in-sample plug-in deviance. So we just use the data that we have to evaluate the deviance of the posterior means. And of course that's being overly optimistic for the prediction error because we're using the data twice, once to estimate theta and then to evaluate the fit to the data. So we add something to the prediction error to make it less optimistic. This is also sometimes called the optimism, but in this penalty term here, the PD, that's the effective number of parameters, and that's basically the posterior expectation of the deviance minus the deviance evaluated at the posterior expectation of the parameters. And here I'm writing lots of expectations, and in practice you would evaluate those when you're doing MCMC as just sample average of your MCMC draws. But I'm not going to write all these sums over MCMC draws to keep the notation simple. Okay, so for the WAIC, the target is the expectation over future data of the log predictive density. So this is also called ELPPD. And we do this we have the same problem. We don't know what the distribution of y is for future data. We don't have any validation data, so we just use the in-sample version of this. And then compensate by using a penalty term twice PW, where PW is the effective number of parameters, which is now approximated by the sum of posterior variances of these log pointwise predictive densities. And the variance, the posterior variance, is obtained by the sample variance of the MCMC draws of these log conditional densities. And this WAIC is appealing, and also kind of, it helps interpreting it to know that it's asymptotically equivalent to leave one out cross-validation, because leave one out cross-validation has the same target. It's also trying to approximate minus twice the expected log pointwise predictive density. And so the important thing here is, in the target, is that the data we condition on in order to learn about the parameters theta, so in the posterior we condition on the data that we have, but we evaluate the predictive density on different data, new data. So that's kind of the essential idea of this leave one out, that we want to base the posterior distribution on the data except for the unit for which we want to make the prediction. Yeah, so in that sense you can see that that's trying to, we now don't have to penalize for using the data twice. So this y minus I is the data except for all the units except unit I. That's kind of the training data from which we learn about theta. But you can see that to implement this is computationally prohibitive, because we would have to run MCMC for each of these training data sets. So it's only really feasible for very tiny data sets like the famous 8 schools data, where we would only have to run this 8 times. So what's done in practice is some PSIS, Pareto smooth importance sampling. And the idea of importance sampling is that we can get away with doing MCMC only once. So we're using the wrong posterior conditioning on all the data, but then we compensate for that by having this importance ratio here, which is the posterior that we want divided by the one that we're using. But doing this properly, or doing this sort of naive way, can be very noisy, so that's why this Pareto smoothing is needed. And I'm not going to go into details because there's a very nice paper you can refer to by Vitari, Galvin, and Gabri, 2017. Okay, but I'm going to apply these ideas to hierarchical Bayesian models. And these are defined in stages, so in this case 3 stages. And I'm going to illustrate by using a multi-level modeling example, starting at the last stage. So the model for response I, J, for unit I in cluster J, so it's going to be cluster data, is a normal, the model is basically a normal distribution, with mean alpha plus zeta j and variance sigma squared. And the important thing here is that zeta j has a j subscript, so it is a varying parameter, or in this case we can say it's a varying intercept. And this parameter has a normal prior distribution with mean 0 and variance psi. And what makes this a hierarchical Bayesian model is that the prior for this parameter zeta depends on the parameter psi, which we then call a hyperparameter, and we can learn about this parameter in the prior from the data. So if you're not Bayesian, this actually completes the model formulation. And the only thing that a non-Bayesian or a devout non-Bayesian would be worried about here is that there is a random parameter, zeta j. And the way they would get around it is by calling it a random variable instead. And because it's not observed, it's a latent variable. And in many ways, I think it would be useful if Bayesians would use that term, because it's a special parameter. It's a bit different than the other parameters. We can learn about its distribution from the data. Okay, but to make this model fully Bayesian, we have to specify priors for all the parameters, including the hyperparameter psi, and that's called the hyperprior. But in this talk, I will use some generic notation for these kinds of models. So I will just use FC for the conditional density of y given zeta, and the other parameters, so all the other parameters except for psi are in the vector omega. And then I'll use G for the prior for zeta given psi, and then P for the other priors. And zeta j could in principle be multivariate, so therefore it's bold. These are sometimes called direct parameters because they enter the likelihood directly. They could be varying intercepts or varying coefficients, as we've seen in a multi-level model. But generally, they could be latent variables in structural equation models or IRT. And in that case, cluster data has a slightly different meaning. So if you, in item response theory, the cluster would be a person. Y is a multivariate vector for responses to different items. So the units I become the items and the person becomes the cluster. And in a Bayesian setting, it's sort of ambiguous whether you think of zeta j as parameters or latent variables, but I think typically you think of them as parameters. Okay, so for this hierarchical Bayesian model, there are two versions of the likelihood. The conditional likelihood is conditional on the latent variable zeta. So it's the product of cluster contributions, and the cluster contributions factorize into a product of unit contributions, because given the latent variables, the responses are conditionally independent. And this is kind of the natural definition of the likelihood in Stan or other Bayesian software. In the model block, you would do, I saw a bit of the tutorial, you would say Poisson, Y is Poisson or something. And that would be conditional on zeta. In contrast, in the marginal likelihood, we integrate out the zeta. So it's marginal over the latent variables, not marginal over everything. Like in Bayesian terminology, sometimes you would marginalize over everything, like in the base factor. But here we still condition on the parameters omega and psi, but we integrate over the distribution of the latent variables. So this is the prior of the latent variables. And this is the likelihood that's used in maximum likelihood estimation of these models. So if you use Elmer and R, that's what's being maximized. And the only parameters for non-Bayesian are the omega and psi, because the zetas are latent variables. So in a way, in the conditional likelihood, we're treating the zetas as if they are parameters, and in the marginal likelihood, we're treating them as if they are kind of missing data. Okay, so in the example that I looked at, the kind of random intercept example, the marginal distribution has a closed form. It's basically for one cluster, the responses, let's say students in a school, the joint probability of all these responses is multivariate normal with mean alpha and variance psi plus theta squared, and with covariance is psi. So the correlation between any two students would be what you may know as the intra-class correlation, psi divided by psi plus sigma squared. Yeah, so that's the marginal likelihood. Okay, so since there are two versions of the likelihood, and therefore the deviance, then obviously there will be two versions of the DIC. One, in the conditional DIC, the definition we saw before, we just plug in the conditional likelihood everywhere where we see a likelihood. And so this is what's produced by most Bayesian software. In the marginal DIC, we just put in the marginal likelihood everywhere. And this requires additional computation because the marginal likelihood is a bit more complex. So it's not really available in most Bayesian software. But our co-author, Merkel, has implemented this in Laban, which is an R package that exploits the R package Laban, which is for structural equation modeling, to evaluate the marginal likelihood for given draws of the parameters. But when the likelihood is not tractable, for example, when you have binary responses, then you can use adaptive quadrature, and we've developed a version of that that's very efficient when you have MCMC draws available. Okay, and basically Dan will use that in the IRT example. Okay, so for the WAIC, there are two versions now in this hierarchical Bayesian model of the predictive distribution that's so central to the WAIC. The most obvious one is probably the posterior predictive distribution, where we just take that conditional predictive distribution given zeta and integrate that over the posterior of omega and zeta given y. So, and we can get rid of the psi here by integrating it out. But really what I want to show is in blue that this posterior of y given zeta, of zeta given y, even after we condition on omega and psi, which themselves obviously we learn about these from the data, even after we condition on them, zeta j depends directly on the responses that we have for cluster j. Yeah, so that's an important thing to remember. So when we use the posterior predictive distribution, we're really checking how predictive our model is for new units from the existing clusters, because we're learning from the existing clusters via the data that we have for those clusters here. Whereas if we use the marginal posterior distribution, so this thing in square brackets, if we use the marginal posterior predictive distribution, what that means, this is the mixed predictive distribution, this was introduced by Gellman, Meng, and Stern in 1996. The idea here is that we use the marginal likelihood instead of the conditional likelihood. And if I expand out the marginal likelihood into this integral, you can see that now zeta comes from the prior, so we're not learning about zeta directly from the data we have for the cluster J. So this effectively is a prediction for a new unit in a new cluster. So if you were, for example, doing posterior predictive checking, then for the posterior predictive distribution, you would be using the posterior samples of zeta, but then generate new data y. But if you use the mixed predictive distribution, then you use posterior samples of omega and psi, but you would sample new zeta. And then given the new zeta, you would sample new y. Yeah, so that's the mixed predictive distribution. And that's appropriate for inferences for new clusters, because we're not conditioning directly on the responses we have for the cluster. Okay, so correspondingly then there are two versions of the WAIC. The conditional WAIC uses the posterior predictive distribution. So we're learning directly about zeta j from the data we have for cluster J. And therefore this corresponds to leaving one unit out, cross-validation. So that's LO, low UO, or something like that. This corresponds to, we're leaving out the unit in learning about zeta and omega, but not the entire cluster. In contrast, if we do, and this is what you get automatically if you use Stan together with a loop package. But the marginal WAIC uses the mixed predictive distribution here. So here we don't learn about zeta j directly from any data that we have for the cluster. So it's much closer to leaving the entire cluster out in the leave one out method. And so we call that LOCO, leave one cluster out, cross-validation. And this one we can compute also using the loop package, but we have to provide the marginal likelihoods, which can be sometimes difficult to do, but it's automated in Blavan now. You can ask Blavan to do it for you. So is this ever used, this marginal version of the WAIC? Well, it is actually hinted at in several places, for example, in Gellman, Wang, and Vitari, that there's a distinction in hierarchical Bayesian models about how you define these things, but it has been used for unclustered data by Lee et al. And Miller et al. But as far as we know, it hasn't really been used for clustered data. But there's so many people in the audience, so maybe you can correct me. Somebody can correct me on that. You will see an application of this to clustered data presented by Dan in a minute. But before that, I want to make a few comments about the special case of unclustered data. So just 2 slides before he takes over from me. Okay, so in the unclustered case, this posterior predictive distribution really collapses to the prior predictive distribution. Or if you want to leave one out, there's no distinction between leaving a unit or a cluster out. Yeah, so these things kind of... so here, if you look again at the posterior predictive distribution, if we want to make predictions for new data yj, then we can't condition on that exact data point. So this is exactly what I wrote before, except for the I subscript. We can't condition on this yj, because we don't have it, we want to predict it. So, so we get rid of that. And then once we don't condition on yj, then zeta j also becomes independent of omega given psi. So then we're back to the expression for the mixed predictive distribution. So really, it doesn't actually make sense to do PS-IS LU with the conditional likelihood. And this point was made by Miller 2018. That's a paper that's still in press that we actually just discovered in preparation for this talk. And they make that point very strongly, that this whole concept of leave one out, if you leave the unit out, then you don't have any information about zeta j, then you can't really use the conditional likelihood. It has to be the marginal one. Okay, so just a brief example that many of you will be familiar with is the 8 schools data, which is like a meta-analysis. So for each school we have one data point yj that represents an estimate of an effect size, namely how effective some SAT preparation program has been. And then we have a sigma j, which is the corresponding standard error. And we use a kind of random effects meta-analysis where we allow the true effect sizes zeta j to vary with variance tau squared, and mu is the overall effect size across all the 8 schools. So the conditional likelihood is very obvious. It's just a normal distribution with mean zeta j and variance sigma j squared. And the marginal likelihood also has a closed form here. So when we integrate over zeta, the mean for the marginal likelihood is the population mean across the 8 schools, or across the population of schools, more than 8 maybe. And the variance is tau squared plus sigma j squared. So in the paper by Vitari, Gelman, and Gabri, they found that the tau squared supported by the data is fairly small, and for that case it's difficult to see much action. So they also kind of faked the data a little bit by just multiplying by some scale factor s. And when you keep sigma j squared, that means that the data, that it looks like tau is larger. So the posterior draws of tau will be larger, and the priors for zeta will be more weak. So when they used a scale factor of 4, they found that the difference between the WAIC based on the conditional likelihood and the leave one out is really large. So 68 versus 86. So the WAIC becomes a terrible approximation to leave one out. And they did leave one out exactly because it's only 8 schools. So we found the same thing. But when you use the marginal WAIC, which was not considered by Vitari et al. In 2017, then you actually get something that's pretty close to the leave one out cross-validation. Okay, so I'm going to hand over to Dan now.
Oh, that's okay. Hi, everyone. All right, so I'm going to talk over an example of using marginal information criteria in the context I usually work on, which is item response theory models. The example model I'm going to work with is the latent regression Rush model. Briefly, it's a model for the probability that somebody responds to a question, say on a test, correctly, given some person-specific parameters and some item-specific parameters. So the probability of a correct response is y equals 1, or an incorrect response, y equals 0, depends on a person-specific parameter, that is theta, which is the ability for person J, and an item-specific parameter, that is delta, the difficulty for item I. So the probability of a correct response is then the difference between the two passed through an inverse logit link function. The latent regression part of the model comes in the prior for theta, where it's assumed to be drawn from a normal distribution with a mean that depends on this regression prediction. So x is a vector of person-related covariates, and lambda is a vector of regression parameters. Lastly, we also estimate the standard deviation for theta. As an aside, we have a web page put together for education-related examples in STAN. It includes links to articles, also some case studies and tutorials we've written, as well as linking to my R package for IRT using STAN, which is called EdSTAN. When I use adaptive quadrature to get marginal likelihoods, it's convenient to reformulate the model in this way, though it's mathematically equivalent to what I just showed. What I've done is replace the person ability parameter by a combination of these two things. We have the latent regression prediction again, and a person-specific residual, zeta j. Being a residual, zeta j has a prior mean of 0 and the same standard deviation as before. I've also put on the slide the other priors for the non-hierarchical priors. When I write T3 here, what I mean is a student T distribution with a shape parameter of 3. I consider these to be weakly informative priors, except of course for the regression coefficients, what's weakly informative depends on the scale of x, so that's something we have to keep track of. So to obtain information criteria in this setting for AIC or the leave one out approximation, what I need is the likelihood for each observation at each posterior draw. So in the conditional case, that's given here, and that is equal to the probability I just showed on the last slide. The only difference is I'm plugging in parameter values of their posterior draws. That is this S subscript indicating the posterior draw. For the marginal case, there's a change in the unit of analysis. The marginal likelihood is for clusters. In this case, a cluster is a person. Each person sort of owns a cluster of their responses to the various questions. So to obtain that marginal likelihood, we use the conditional likelihood for a person's response to a question and multiply that over all the questions for a given person. Then we integrate out the residual from that product and over its prior distribution. And that gives us the marginal likelihood. So the marginal likelihood depends on psi, which is the standard deviation of the residuals, whereas the conditional depends on zeta, the residual itself. Of course, it's not so easy to do that. Because it's a logistic model, there's not an analytical solution for that integral. So instead, we use an adaptive quadrature scheme. For that, we need a few things. Firstly, we need the posterior mean and the posterior standard deviation for each residual. So let's call those mu and phi. And then we also need a set of standard Gaussian quadrature nodes. These can be obtained from several different references. I use an R package StatMod to get them. The gist of this is it's just kind of like approximating a standard normal distribution with a histogram. So each adaptive quadrature node M has a weight, we'll call that W, and a location, we'll call that A. What I'd like to do is adapt them to put them closer to the posterior for zeta. So to do that, I update the location like this, changing the scale by multiplying by the posterior standard deviation for the residual, and then adding the posterior mean. Having changed the location of the nodes, I also have to change the weights, and I do that using this really ugly equation here. I'm not going to try to walk through it right now, but something interesting about it is that it depends on psi, the standard deviation of the residuals. So that's a parameter in the model, and it changes from iteration to iteration. So what's kind of neat about that is that the weights change between posterior draws for a given cluster, but the node locations are always the same for a cluster. Anyhow, having those adaptive quadrature nodes, we can approximate the marginal likelihood like this. We again have the conditional likelihood, but instead of plugging in zeta, we plug in the node location. Multiply that together for each item a person responded to, and then weight that by the weight associated with that node. Do that for every node and add them together, you have an approximation for the marginal likelihood. So let's use that to obtain marginal information criteria. I'm going to use this example data. It's the verbal aggression data. It's based on a questionnaire given to people to assess their propensity towards verbal aggression. It has 24 questions on it. An example is, a bus fails to stop for me, I would want to curse. So each question has this frustrating situation, and then a possible reaction to that situation. People responded to those questions with either yes, perhaps, or no. And I've coded yes and perhaps as correct. It's correct if you're verbally aggressive. And then no is coded as incorrect. 316 people responded. They filled out this questionnaire. And as I mentioned, there is 24 questions. Along with that are 2 covariates related to the people. The first one was an indicator variable for whether or not the person is male. I've changed that to be contrast coded, so it takes a value of 0.5 and negative 0.5. The other variable is their score on a separate measure of what is called trait anger. And I've likewise recoded that. It now has a mean of 0 and a standard deviation of 0.5. I did that so that the parameters in lambda, they will be associated with variables of the correct scale, so now that prior will be sensible. What I will do is fit 5 different versions of the latent regression Roche model. The difference between them will only be what covariates I put in. So the first model will have no covariates. It's just going to include the intercept in the latent regression. The second model includes the anger variable. The third, the male variable. The fourth includes both. And fifth includes both and their interaction. I'll obtain 10,000 posterior draws for each model, and that's a huge number. It is a great deal more than is needed to get an accurate understanding of the parameters. However, these information criteria are highly susceptible to Monte Carlo error, and so I'm obtaining a huge number of draws to stabilize those estimates. I'm going to get both conditional and marginal information criteria, and for the marginal case, I'm going to use 11 adaptive quadrature nodes. Lastly, I'm going to replicate all of this 10 times, so we can see in an empirical sense how much the results vary due to Monte Carlo error. And here are results. I'm showing information criteria estimates for DIC, WAIC, and the leave one out approximation. On the top is for the results for the conditional versions, on the bottom for the marginal. And then along the x-axis, results for the replications are clustered by model. In the marginal, let's start with the conditional. In the conditional case, the information criteria estimates still have a high degree of Monte Carlo error even after the 10,000 posterior draws. So if you're doing this sort of thing where you use information criteria to pick a favorite model, you're going to have a bad day in the conditional case. You'll select a different model every time you run the analysis. It happened to me, that's how I know this is a problem. In the marginal case, we have a good deal more stability, but it did require 10,000 posterior draws to get there. However, we can say that consistently model 4 is chosen as the favorite. So the marginal case has this better property that it's more stable. But for this particular problem of trying to choose a set of predictors related to the persons, it's also the only one that makes sense. The conditional information criteria are making an inference about the predictive accuracy of the model, but it's as though the model is going to be fit to new data from the same people and the same questions. What I need is the inference that comes from the marginal case, where I'm marginalizing over the person distribution. So I'm making an inference about new data that might come from new people. So since I'm using a latent regression on those covariates, that's the relevant part to look at. Lastly, we can look at, rather than the whole of the information criteria estimates, just the penalty parts, or what you might call the effective number of parameters. So this plot is laid out in the same way as the previous one, but I've added to it horizontal lines to indicate the number of parameters in focus. Or another way to think about that is the maximum the penalty term we would expect to be. So for all the conditional models, the number of parameters I would say that are in focus are 339. That is 24 parameters specific to the items and 316 parameters specific to the persons. -1 because I constrained one of the item difficulties. All of the results for the conditional case are well below that. And the reason for that is that prior information reduces the number of effective parameters. And for the person-specific parameters, we have that hierarchical prior that is informative. So the number of effective parameters is reduced to noticeable extent. In the marginal case, the number of parameters in focus varies from model to model. It's the count of the item parameters plus the latent regression parameters, plus the parameter for the standard deviation of the residuals. So that'll vary between 25 and 28, depending on the model. And for the marginal case, the actual estimates obtained are much more similar to the number of parameters in focus. That's what I've got from my section.
Okay, so I guess the just brief conclusion is that it's important to make an informed decision between marginal and conditional versions of the information criteria, but people just tend to do what comes out of the software without being aware of the issues. We would argue that the marginal information criteria are generally more justified than the conditional ones. One reason is that maybe the second one is more useful, as Dan mentioned, that we want to generalize to other people in the case of IRT, especially when our model, an important aspect of the model we want to evaluate is what predictors to use for verbal aggression. Then we want to see how predictive those predictors are for future people, right? Not for the people that we have in the data. So, but also, so basically when we want to evaluate the form of the prior for zeta, which may include covariates, then it seems like we have to use the marginal version of the information criteria. There are also theoretical problems with the conditional version of the information criteria. One of them I talked about very briefly. In the unclustered case, it doesn't really make sense to think of it as some kind of leave one out cross-validation. There are also two problems I didn't mention before that were pointed out by Millar, and that is that the conditional version of the WAIC doesn't meet the regularity conditions that are necessary to show that asymptotically it reaches the right target. One of those conditions is that the distribution of those pieces of data has to be identical. The pieces of data have to be identically distributed, but the conditional distribution depends on zeta j, so zeta j is often the mean, so each zeta j has a different mean. And the other problem is that the number of parameters increases with the sample size. A similar issue has been pointed out by Plummer in 2008 for the DIC. When you use the conditional version, that, again, that the number of parameters increases with the sample size, and therefore the penalty term doesn't approximate that optimism very well in using the data twice. So I think that's related to the incidental parameter problem in maximum likelihood, when the number of parameters increases with the sample size. And then Dan illustrated or showed that there are some empirical problems with the conditional information criteria, that they have even larger Monte Carlo errors than the marginal ones. That was even more pronounced in the SEM example that we discussed in the paper that goes along with this talk. Okay, I'm just going to really not be much longer now. And then also that the WAIC is a poor approximation to the leave one out. That was also something you could see in Dan's slides. Okay, so here are the 3 key references to other people that relate to our talk. The first 2 talk about marginal versions of WAIC, but in the case of untrusted data. And the last one you probably all know, because it's the one that Blue is based on, the R package. And then here are the other papers, but I don't have time to linger on much. And this is the paper that goes with the talk. It's going to be an archive any minute, just putting some fun finishing touches on it. And much of this work is based on Dan Furr's dissertation, and the Blavan package is published or is in press, something about it, etc. And really, this was another mention of that website on education examples, where you can find some of the code, and I guess we'll make the code available that relates to the talk there and so on. But I would also like to ask you if you have any case studies, or if you know of any papers that use Dan in education research, we would like to link to those things on this website. So, thank you. So I think we have time for questions.
Thank you, Sophia and Daniel. Does anyone have any questions?
I'm going to let everybody else go first, because we have a lot of questions for everything.
Charles?
Okay.
Charles, right here.
Okay. Oh, no, go ahead. For another development.
Hi. The question I had is regarding using conditional or marginal information criteria. It seems that it depends on whether I want to make predictions for new individuals or predictions for the individuals I already have data on. And since I'm going to be using different information criteria, does that mean that I might be using a different model for within and out of sample predictions?
Okay, so for out of sample predictions, if you leave the cluster out, you automatically have to use the marginal version. For in sample predictions, you have the choice between the marginal and conditional versions. And then I think you would have to choose the one that's appropriate for the inferences you want to make. So if you want to generalize 2 new clusters, you would use the marginal version. And I'd like to mention there's a paper by Gelman and Wang where it's a hierarchical Bayesian model where the clusters are actually state and income bracket combinations or something like that. And it's to do with voting predictions. And then I guess you want to predict for these states and these income brackets. So that's an example where you probably don't want to use the marginal. So they correctly there use the conditional version of the information criteria.
So we're about to add a one-dimensional integrator to Stan. Would that let you get rid of this approximate node-based thing that you've got?
So you're saying your one-dimensional integrator is not approximate?
Well, it's a numerical integrator, but we'll be able to control the error in it.
Okay, yeah, so with adaptive quadrature, that's also what we can do. So we can choose the number of nodes, and so we can make the error small. But we're thrilled if Stan does it. That's great.
Yeah, that should be coming very soon.
I don't know how you make it adaptive, though. Because I don't know the posterior, the locations for the residuals until after I fit the model.
Well, if the user can, if it's straightforward to use your one-dimensional integrator to evaluate these marginal likelihood contributions, then it will be useful. Yes. Yeah, it will be extremely useful.
All right, we have time for one more question. Anyone? No, if not, thank you very much.